Okay, welcome to lecture 12. So basically last time we sort of stopped in the middle of something, so I'll continue from there. But if there are any questions about what we did last time up to the point we reached, please let me know. So I'll just remind you of a couple of formulae which we'll be using. So we derived from directly from operator approach the answer for the propagators in two cases. So u for the free particle is root of m over 2 pi I h bar t times the phase upon 2 h bar t. And u for the harmonic oscillator is equal to again a square root formula and an exponential okay. So as a test of whether sorry?
For the correction you made yesterday.
minus 4x.
No, I did not make any correction minus 4, I'm
Okay.
sorry.
Okay.
I did not. People said I should be minus 4, but it's not. What I had written yesterday was xi plus xf whole squared, which was wrong. Then I corrected it to xi squared plus xf squared. And if omega is 0, then this thing correctly becomes xi minus xf squared. Okay. Now we are going to try and use path integral to obtain the same result. And we got some part of the way, and we concluded from the path integral. So let's look on this side. So we said that this u is equal to a path integral over x some measure, which we'll try to avoid specifying, but we'll try to discover what it should be, times this. And this, when we insert the expansion of x around x classical, gives me a phase factor e to the I s classical over h. So s classical means s of x classical. Later on I'll just call it s classical for short. So it's the action evaluated on the classical solution. Okay, and then there's still an integral, and it's over the fluctuation. And then what happens? Yeah. So this integral is over the fluctuation, and the integrand is e to the minus half dt prime eta of t, then the operator O of t prime eta of t prime. By now you probably realized that O is a differential operator acting on some delta function, and that allows us to do one of the integrals. So in fact this whole thing could as well for short be written integral dt eta O eta of t. Okay, where here we understand that eta is at t, this eta is also at t, and this O is a differential operator which directly acts on eta. If you have tried to work out this step, you would have noticed that it's exactly this. Okay, for example, when O was second derivative of delta t minus t prime, then after doing the t prime integral, O became second derivative of that. So this is just del t squared up to some factors. So it's for short we can write this, and we finally conclude that it should be e to the I s x classical by h bar times det to the minus half of O by 2 pi. Okay. Now this is sort of an unambiguous factor. You will see that, as you can see, this is definitely a phase. Of course, there could be some imaginary part there also, we don't know. But this is an overall phase for sure, because the action will be real on action is always real, so it will be real on a classical solution. And we worked out this action for the case of a free particle. And for the free particle, I think we concluded by noticing that S x classical is precisely everything that appears there except I by h bar. So it's m by 2t xf. So even 2, I think, no, 2 is there. So this is this, and this is an independent calculation, just a classical calculation, and it reproduces an important part of the correct answer. So it remains to find out this part. So the rest of this is det to the minus half O by 2 pi. Now I'll point out here that we are being a little brave putting this 2 pi, because it could be anything else, because we didn't say anything about the normalization of this measure. So if you have some measure and I have twice the measure, or 10 times the measure, or million times the same measure, so even though the measure is a subtle thing, but we all agree, let's say, how to do it, but we disagree by some factors, then those factors would work their way into the answer. So an overall constant is going to be difficult to fix. That we anticipate. Nevertheless, we can try to see how well we can evaluate a determinant and what sort of sensible answer it gives us. Okay. So to evaluate the determinant, so now for now I am putting this away. I'll come back to this later. So to evaluate the determinant, and yes.
There is no multiplication there, right?
Where?
Determinant that x classical you have written.
Sorry.
Yeah.
I wrote it in the wrong place, completely wrong place. This is not there. Yeah. This is correct and S classical is that. I already wrote this. I unnecessarily wrote it again. This is correct. So this is what we want to now work out. Okay. For this purpose, we need to know the eigenvalues of O. And for that, we need to write the eigenvalue equation. It's dt prime O of t and t prime psi n of t prime is equal to lambda n psi n of t. And now we are going to do it for the free particle. So up to now everything I'm doing is for the free particle. And so this O we had already written down. It is Im upon 2h bar, and then this is integral dt prime del t squared of delta t minus t prime psi n t prime. Okay, and now as I mentioned many times, we basically have to note that the derivative, so the rule is that if I integrate in t prime this quantity, it gives me the second derivative of this guy. Or I can exchange this derivative in a del by del t prime and then do integration by parts. But anyway, this whole thing works out to be Im over 2h bar del t squared of psi n t. And this, therefore, has to be exactly equal to, keep losing my page, just trying to keep the factors straight, which I often lose. Yes, is just lambda n times psi n. Now, where have we seen this equation before? So, it's pretty obvious that any exponential of an exponential in t, second derivative will be proportional to the same thing, and what comes down will be the eigenvalue. In fact, this is really the free particle Schrodinger equation all over again in a different disguise. Okay, mathematically it's the same equation, because in Schrodinger's equation you have a wave function that depends on x, and you have h bar squared over 2m del by del x squared in 1D. So you just rename everything, change the constants, and it's the same equation. So whatever we knew about Schrodinger equation works here. And in particular, we have to keep in mind the boundary conditions, which are psi n of 0 equals psi n of t is equal to 0. Where did we get this boundary condition from? It's the same boundary condition as the one satisfied by eta. Where did we get that from? We expanded the original x over x classical plus eta. Since x classical had the correct boundary conditions, eta has vanishing boundary conditions. One thing you should remember is that when we say an operator O, for example, is like this, we haven't said enough to tell you what the eigenvalues are till we tell you what space of functions the operator acts on. And the space of functions that it acts on is those functions which vanish here, which have these boundary conditions. And that's because here it acts on functions with those boundary conditions. Etas have those boundary conditions. So the eigenvalue problem is the nature of the eigenfunctions is inherited from these etas. Okay, if I had different boundary conditions on eta for any reason, then I should look for the solutions of this equation with different boundary conditions, and then the eigenfunctions would be different, the eigenvalues would be different, the determinant would be different. So defining an operator requires to know what type of functions you're acting on. But here we are very clear, because etas vanish at the endpoint 0 and capital T, so psi n also must. So what Schrodinger equation is this then? What physics problem is this one? Particle in an infinite box, I mean infinitely high box, where the wave function vanishes on the boundary. And we know that the eigen functions there are sine functions with the right coefficient, so that they vanish at the ends. So we immediately have it. Only thing is, of course, these are constants are a little bit different, so you have to account for all those things. But it's one step to write down the solutions. They should also be correctly normalized on the interval, although probably we won't need that. So 1 by root t sine pi n t by t. N is 1, 2, 3, dot, dot, dot. So this vanishes at small t equals 0 and capital T, and these are complete set of functions. And now if we act with del t squared on these, we pull out pi n by t squared, then we multiply with this, and that gives me the eigenvalue. Yes?
So why do we need to normalize them? Because like eta t, like with a different scaling would be a different solution.
True. Yeah, actually we don't need to normalize them at this moment. We're not going to use that. But in general, it's good to have the normalization ready, because, well, there are other ways to do this calculation, but in this calculation we won't need to normalize them. So we just need lambda n actually, and lambda n immediately come out to be minus im over h bar pi n by t squared. So this minus and this thing squared comes from differentiating sign, and im upon h bar is from there, and what happened to the 2 I don't know. I seem to have lost the 2, because I think there was never a 2. Why was there never a 2? Because the operator never had a 2. This was my mistake. Because we always wrote the exponential as e to the half eta o eta. So the operator didn't contain the 2. The half was written outside. So there was never a 2 anywhere, and so there is no 2, and therefore this is the answer. Good. Once we have the eigenvalues, what do we need to do? Well, det of O is product n equals 1 to infinity minus im upon h bar pi n by t squared. So what do you have to say about that? Not as nice as we might have hoped. It's clearly highly divergent product because we are taking the product of n squared from 1 to infinity, and moreover we are multiplying it with this factor also raised to infinity. So it's pretty bad. Doesn't converge. That's very bad. Okay. So again, we need to be optimistic. I can't emphasize enough how much optimism is important in these things. That at every stage, nature gives us, or the physics gives us, or mathematics, whatever, gives us enough reason to give up and go home and cry. But that's not what people do. And the best way at this point to figure out, so there are many ways to figure out what to do next. Okay, there are actually, I could count at least 3 different ways. So let's go over them one by one. One of them, yes. Question? Sorry. Okay. So one way would be to say, look, we know from the path integral that u is equal to some unknown factor, I don't want to call it, normalization factor times e to the I m by 2 h bar t xi minus xf squared, and it's n which is giving us the trouble. It's the determinant and we are not able to calculate it. But there's a clever way to fix n without calculating it. What would that be? There's a formula which will help us to fix n. I made a comment very early in the game that propagator comes with a fixed normalization because of a certain relation that it obeys. What relation is that? Composition law. So composition law says that u x f x I is equal to integral dx bar u x f x bar u x bar x I. Right? And this cannot possibly be true for different normalizations. Let's say it's true for one particular answer of u, then even multiplying that answer by 2, this will be wrong. It's quadratic on the right side. It just can't always be true. So this is a way to actually fix n. And we can apply this. So we can say, look, we used S classical to get this factor. Our methods with determinant didn't work to get this factor. So we are just going to use composition law. And if we do it, what do you think is the answer?
So we already have the answer, no?
We have the answer, but we calculated it from operator quantum mechanics. Now we don't want to use operator quantum mechanics. That is the important point. We think of path integral as self-contained. But path integral doesn't want to be that self-contained. When we ask it to be self-contained, it returns some nonsensical answers like this. But we keep trying to box it in and make it self-contained. What we won't do is we'll never rely on operator quantum mechanics. But we can rely on principles of quantum mechanics, one of which is the composition principle, which simply says that if this is really a physical probability, then it should be composable with an intermediate point x bar. So I should be able to plug this answer in here. Remember, this part of the answer we derived using path integral. This we did not assume using canonical method. This we derived because it's S classical. Okay, so this we are entitled to use and it will go in. And remember, this is where the dependence is on x. So this will be x f minus x bar squared, and this will have x bar minus xi squared. And then you'll multiply them and you'll have to do some manipulations to do the integral over x bar. Okay, and what do you expect you'll get when you do this? The correct answer. There's no other answer you can possibly get, because we already know that this satisfies the composition principle. So if I apply composition principle with an unknown n, the only option is that it fixes n to be root of m over 2 pi I h bar t. There's simply no other option. It has to work, and it does work. You can also do it and check that it works. Simply use this structure, do this integral, and require it to be back to equal to this. So this side will have an n, this side will have an n squared. So you will get something times n squared is equal to something times n. that will allow you to solve for n, and you will get this. So this is one way. So this is self-contained in the sense that we didn't use operator quantum mechanics. Okay. I might sound like a stuck record, but we always want an answer by whatever means, hook or crook. Okay. This is not crook. We are using known principles that we believe in. If it failed, if it was wrong, it would mean that something is wrong. Either path integral is wrong or composition principle is wrong. But we'll keep believing they are right as long as we can get sensible answers, and here we do. So we should be happy. Okay, so this is one method to find the prefactor. But we shouldn't give up on the determinant. We have a nice formula. It just happens to diverge. So let's put the formula aside for now, and we'll simply say that det O of the free particle is equal to product n equals 1 to infinity minus Im upon h bar pi n by t squared, and pray for some miracle which will help us to evaluate it. But for some time, to give us some distraction and something to do, let's switch to the harmonic oscillator and ask the same questions. Okay. So in the harmonic oscillator, our first job is to find x classical. And that's easy to find because harmonic oscillator equation is very easy. The solutions, so in the free particle, the solution of the differential equation was constant plus linear in time. Now it's not constant or linear in time, it's sine and cos of omega t. That's the basis. And then you have to simply fix that it has the right boundary conditions, namely it starts at xi and ends at xf. And so the answer is very easily found to be this plus sorry, that's not what I meant to write. And this was meant to be t. So it's this number depending on the boundary conditions times the cos function, and this number which also depends on boundary conditions times sine function. It's clear that it's linear combination of cos and sine of omega t, so it will solve the harmonic oscillator equation of motion, no question. And at small t equals 0, this is 1 and we get xi, this is 0. At small t equals capital T, we get a term from here, but it cancels the term that comes from here. And xf, this sign and this sign cancel, and we get xf. So it's just rigged up to do that. And now we can plug that into the action of the harmonic oscillator. These are all exercises for you, and you find, no surprise, I won't even bother to write it again, you get the correct phase again. So this is again the exercise of finding the phase, the classical action part and the determinant part separately, and the classical action has worked. So what's next? Now we have to tackle the determinant of the harmonic oscillator problem. And what's very nice is that the problem isn't very different. So for the determinant of O, so we have to calculate det to the minus half O of harmonic oscillator. I keep writing this 2 pi, but really I feel dishonest writing it. Anyway, so to calculate this, the eigenvalue equation, which is again a Schrodinger type equation, is Im upon h bar del t squared plus omega squared. Psi n of t is lambda n of t, psi n of t. Okay, because what was the operator O in the harmonic oscillator case? It was del t squared acting on a delta function and then omega plus omega squared. People are looking very blank, so if you want, I'll write that operator again. O t and t prime harmonic oscillator, I believe we wrote it last time, is I wrote it, it's this operator. It's Im by h bar del t squared plus omega squared delta t minus t prime. So if I put that into the equation with the with the integral over t prime, then I get this. Any problem? It's okay? Yes.
Why do you not consider the lambda n equal to 0 solution?
Lambda n equals 0 solution of which problem? This one?
Free particle.
Free particle. At lambda n equals 0, n is 0, so the wave function is 0. So how is that a valid wave function?
That was not the wave function, yeah. It was the fluctuation.
No. I'm trying to solve a different. I'm trying to solve an equation. So sorry, I used the word wave function for this eigenfunction. Only non-zero eigenfunctions are allowed, right? There's nothing like a zero eigenfunction of an operator. Every operator acting on 0 gives me 0, but that doesn't mean 0 is an eigenfunction of that operator. You agree that if n is 0, then the psi n of t is 0?
Yeah.
Because it's sine of pi n something. So if n is 0, then psi n of t is 0. That's not an eigenfunction. Huh?
What is the problem there?
What is the problem there is that 0 is never an eigenfunction. There's no such thing as eigenfunction 0. It's like supposing I have a 2 by 2 matrix. How many eigenvectors are there? For a 2 by 2 matrix, Hermitian matrix, there are 2 eigenvectors. Okay. Let's say I take sigma 3. So it has eigenvector 1, 0 and 0, 1. Now I'll give you a third eigenvector 0, 0. Is that an eigenvector? It's like taking 0, 0 to be an eigenvector. This is the eigenfunction has to be a non-zero thing, otherwise it's not an eigenfunction. It's part of the definition of eigenfunction. And importantly, that has a consequence. The set of eigenfunctions which I wrote, psi n sine n pi by t, is a complete set. So any function satisfying that it vanishes at time equals 0 and time equals capital T can be written as a linear combination of these for all n from 1 to infinity. That's a complete set. There's nothing more you can add to it. That's why we use completeness. You must have heard of completeness in quantum mechanics. No? Completeness never came up in your courses. Complete orthogonal basis. Yeah? But I don't know if you ever appreciated why we talk about it. We talk about it because it tells us when to stop making the basis. Once the basis is complete, nobody can add anything more in the basis. That's the end of it. Okay? This is complete on the interval 0 to t with vanishing boundary conditions at 0 and t. Therefore, there can't be any more. In any case, 0 isn't a function, so 0 isn't a valid function because the function, what did I do here? Okay, that was a trivial mistake. 0 isn't a valid function, so eigenfunctions also need to be normalizable and 0 can never be normalized. So from many points of view, that's not there. What can be there is the 0 eigenvalue, which is a completely different thing. Okay, if the eigenvalue can be 0 without the eigenfunction being 0, then we should keep it. Why am I sensing that people are not getting this point or not agreeing? Please express your disagreement. What's the disagreement? No, seriously. What? Is there agreement? No, but you people nod vigorously when there is agreement and you are looking very, very uneasy right now. 0 eigenvalue is a thing, but the eigenfunction better not be 0. So I can have a matrix acting on a non-zero vector, answer is 0. That means the eigenvalue is 0, not the eigenvector. That can happen, and we'll soon see that it does happen, and we'll see how to deal with that. That's a different kind of problem. Okay, good. So now the question is how to solve this equation, and well, it's really trivial because I can write this equation as Im by h bar del t squared on psi n is equal to lambda n minus Im omega squared by h bar I just took this is a constant, so I take it to the other side, and I see that is the same equation as before. Okay, but the new eigenvalues are this whole thing. Instead of being the lambda n of the free particle, they are shifted by that much. Yeah, I think that's correct. I think I have some i's in the wrong place. No, I think I have i's in the right place. Good. Now this is fine. And these lambda n's I already determined. So what were they? So lambda n harmonic oscillator is lambda n free particle minus this stuff. And so this is equal to lambda n of the free particle is that. So it's equal to minus m im by h bar pi n by t squared minus omega squared. Good. I seem to have a sign wrong.
So the lambda and free particle should be equal to lambda and harmonic.
Sorry, correct. Thank you. Exactly right. Exactly. And therefore lambda n of the harmonic oscillator, this has a plus. Sorry, this has the minus sign, which I wrote correctly. Yeah. Because now, if I solve for this, then this term will come there with a plus, and this minus with minus gives me a plus. So I'm good. And therefore, the determinant of O for the harmonic oscillator is the product n equals 1 to infinity minus im by h bar pi n by t squared minus omega squared. And of course, we have the nice feature that as if n is if omega happens to go to 0, then it reduces to the answer for the free particles. So it's self-consistent that way. But now it does have the problem that we raised a minute ago, which is that what if my time interval and pi are such that pi over t when multiplied by some integer happens to be equal to omega? Could happen for some choice of omega. Time interval I will choose in advance. All n's are here because this is a product over all n's. If any of those n's gives me this factor, giving it a value equal to omega squared, then one of the terms in the product is 0, therefore the whole product is 0. Okay, and this is worrying, but we can get around that by saying that we'll keep omega sufficiently generic that it never matches any pi n by t. That's very easy to do. We'll worry about zero modes later.
So,
Yeah.
It's I m by 8, so that one is imaginary.
Yeah, that's here, and then this is a factor.
Oh, sorry.
Yeah. Yeah. We'll also see somewhere what is the root cause of this possibility. It has something to do with the oscillatory nature of path integrals. In any case, this is the answer, and we see that it's very similar to the answer of the free particle. And now we can do something a little creative. We can say, okay, of course it's also divergent for the same reason. Product n equals 1 to infinity of that thing is horribly divergent, but we'll write it here anyway.
So,
Yes.
so that is a product over an infinite amount of complex numbers.
Sure.
So, is there something like the end result can be a real number sometime? Or
It's divergent, so there's not anything. If we want a divergent thing to be something, we have to give a prescription how to evaluate it, and we are trying to give various prescriptions. So now I'm going to give you a new one. One prescription was to forget about it and use the convolution formula, composition formula, and that worked. Okay, but now we are going to find a different prescription, and let's just do it right away. So this is this. And what we are going to say is, look, it seems that we can't evaluate the determinant for the free particle or the harmonic oscillator, but how about if we try to evaluate the ratio of these two determinants? So supposing I write that, so let's write det of O harmonic oscillator upon det of O free particle. Okay, this is product n equals 1 to infinity. Now this is a prescription, we are manipulating quantities that are ill-defined, but I am saying let's take the ratio and let's define it by taking the ratio of the eigenvalue and only then taking the product n equals 1 to infinity. So it's a prescription. It is no guarantee that it has to work. Okay? Fine. But when I take the ratio of an individual term here and here, this minus Im over h bar cancels, and this term is the same. So I end up getting the product of 1 minus omega squared t squared upon pi squared n squared. Right? And good news, this product does exist. There's a famous formula, I think it's the Euler formula. Which says product over n equals 1 to infinity of 1 minus x squared over n squared for some number x is sine of pi x upon pi x. For now at least, let's not worry how the formula is derived. I don't think it's very difficult, but that's the answer. Okay, so it's finite. So therefore, this is equal to sine of omega t. Sorry, what is it? Yeah, omega t upon pi. No, omega t pi times omega. Yeah, okay, so sine of omega t over omega t. Yes, x is omega t upon pi, so pi x is omega t. That's the formula. Okay. So what does this tell us? It says, well, we wanted to know how to apply path integral to free particle and harmonic oscillator, but suppose we are not good enough to do that. We'll just borrow the result for free particle from anywhere, even from old quantum mechanics, once and for all. But harmonic oscillator, we can derive the result because this ratio is finite, and so I can actually find out the ratio of the propagator of harmonic oscillator to that of free particle. So one new piece of information I've got purely from path integral. Okay, and if this procedure works, then I could imagine that for all 1D problems, I only need to know one of them, namely the free particle, and maybe all other 1D problems I can define the determinant by taking its ratio with the free particle determinant. That means I'm basically finding a way to evaluate the determinant up to some normalization which I fix by hand.
So,
Yes.
how do we know that that normalization will always give a, it's the same sort of
Yeah.
infinity that is blowing up
Yeah.
for every.
So that's why I said all one particle problems with a potential, we expect it to be the same by some sort of continuity. So if you have a potential, you could take that potential. See, harmonic is an example of a simple potential, but if I have a complicated one, I could still take it to 0 and it should give me back the free particle. So in the limit potential goes to 0, this ratio should be 1. So the ratio can't possibly be infinite in the limit when the potential goes away. So therefore I should expect a finite answer. And there can always be surprises. There are also very bad potentials you could think of, like e to the x which blows up or something. But if you think in the space of reasonable potentials, this should work, and I believe it does work. Okay. So now let's see how much we can use this result. Remember that this is a ratio of determinants, but we don't want a ratio of determinants, we want a ratio of det to the minus half. Because that's what comes in our path integral formula. So from this result, we can say that det to the minus half of O harmonic oscillator over det to the minus half of O free particle is equal to root of omega t over sine omega t. Right? And we got this from Euler's formula. Okay, well now you can inspect this prefactor and this prefactor. Is the ratio equal to omega t over sine omega t? It is. So it works. So this is the second approach, and it's an approach that we should often use, that whenever you have a problem where there's a determinant which is ill-defined because it's somehow infinite, we'll define some reference problem where the determinant is fixed to be something for whatever reason, will be a physical reason, and then other problems in that class can be calculated using the path integral, and this is pretty good. Because if you think about it, free particle is not the reason why we decided to invent path integral in the first place. We know everything we need to know about it without inventing path integrals. Can it give us some valuable insight into the behavior of particles in a quartic trap, particles with a spin, particles in a magnetic field, particles doing a lot of other things? And the answer is it can, because whenever we arrive at a determinant in those problems, we'll simply take its ratio with the free particle determinant to fix it. And then we'll hope that whatever the ratio is gives me some finite product or something, and I'll evaluate that. So that's the philosophy.
So,
Yes.
so the constant, like 1 by 2 pi sort of constant. So up to a constant, we have fixed the normalization by taking the determinant.
Yeah, even the 2 pi went away because this was also over 2 pi and this was over 2 pi.
So like we have fixed the normalization even up to that.
Even up to that, we fixed the normalization completely. And of course, since this gives me the correct ratio, it means that it gives me this factor. And we have independently checked, or you should have checked, that this formula also satisfies composition formula. So the circle closes. We already know that this is the correct answer from operator quantum mechanics. We also know it's the correct answer from composition formula. And now we know it's the correct answer by comparison method, comparing this problem with the free particle. So 3 ways we already know. And there's still another way. Okay, yes.
So we are fixing the normalization using the composition rule, right? For free particle.
No, now we are not. We did that and we put it aside. Now we are using something else.
So, but how does that ratio fix the normalization? Like they cancel out, right? Like for example.
No. This one we assume that we know from whatever means. We don't question how we know this one.
Okay.
Okay. But now I know the ratio of these determinants.
Yeah.
So that immediately fixes this.
Oh, okay.
Because the path integral for this tells me e to the I s classical times determinant to the minus half. Path integral for this says e to the I s classical times determinant to the minus half. This I have determined and this I have determined from path integral. This one I say that, well, one piece of information I need from whatever source. Now composition formula or operator quantum mechanics once and for all. Now I determine this. And that's absolutely consistent thing to do. But you can again see that, this requires an optimistic approach, which says that, well, in physics we want to know something from our equations. If we can't know everything, we'll know everything minus one piece of information. It's pretty good. We anyway aren't going to know everything, okay? But we would like to, for example, know all possible 1D particle inner potential problems. Well, we know all of them except the free particle directly from path integral, if of course this works. I haven't proved anything about this. I've only shown you that it works for harmonic oscillator. So we have to think a little more to decide whether it works for more general problems. But at least it's reasonable to hope that by taking this ratio, this infinite growth that we saw in this case and in this case seems to be a feature of the free problem. So somehow by normalizing it out, we get rid of an unwanted feature, and now what we've got instead is a feature of the harmonic oscillator problem, because omega is the parameter of the harmonic oscillator problem, which was not there in the free particle, and that dependence we fixed. You will often find in physics in research papers that instead of trying to get a formula, we just want the dependence of that answer on something. What's the dependence of the answer on omega? Okay, and we got it. So this is exactly how one tries to do things. And here's an operational rule. As a result of this way of doing things, we can simply assign the rule that the determinant The rule amounts to same thing as taking ratios, that we'll define the determinant to the minus half of Im upon 2 pi. This is that 2 pi with which I was dividing O every time. This rule should map this to m upon 2 pi I. Okay, this is the free particle determinant. I assign it to have that value, and all other potentials, all other problems, I'll evaluate with reference to this rule. Of course, if I have particle in multiple dimensions, I have to worry. For example, this will probably come out cubed. If I have fermions in the problem, this won't be the answer. So it's not that simple. But for free ordinary particles, this is the rule which normalizes all determinants. Yeah, question? Okay. Now I told you there are many methods. So here's a third method that I'll go through quickly. And this method uses somewhat heavy duty mathematics and analytic continuation in particular. And the function that it makes use of is the zeta function. So this is called zeta function approach. Yes.
One thing, so when we're taking the ratio,
Yes.
we have some divergent function divided by another divergent function.
Yes, yes.
And that is some finite function.
Yes.
Now we are saying that the lower divergent function is actually a constant.
No, we are saying that you assign it to be a constant. That means if you assign that, see, the divergent over divergent is the correct answer. Now we are simply saying that the denominator should be thought of as being equal to its correct answer, and then in that normalization we evaluate the numerator. We don't divide it by a divergent function anymore. Directly the numerator will be finite. I mean, it's just a way of re-expressing. That rule is just the re-expression of taking the ratio. Okay, so zeta function approach starts with a very beautiful and famous function, zeta of s, which is the sum from n equals 1 to infinity 1 over n to the s. And this is convergent for all complex s satisfying that the real part of s is greater than 1. If it's 1, of course, it's divergent. That's well known, that summation of 1 over n diverges, 1 over n squared converges, but actually in between that space, 1 over n to the 1 point anything also converges. And so this function is defined for that, but it's also defined for complex s only as long as the real part satisfies that. And therefore, it has an analytic continuation which we can use to evaluate this even for s being 0 or negative, where this clearly diverges. Okay, so use the analytic continuation. How are we going to use that? Well, before we use it, let's also write down its first derivative. So if I want to differentiate this in s, this is, remember, e to the minus s log n. So if I differentiate in s, I'll get minus log n upstairs. So this is minus summation log n upon n to the s. Okay. Now these two formulae contain some very interesting information via analytic continuation. So analytic continuation says there is a function zeta of s which is analytic except at certain places, and in places where it looks it might diverge, it still has a value obtained by analytic continuation from the place where it converges. Okay, and those values I don't have to calculate. I can look up a book or a table of zeta function values. So for example, the analytic continued zeta satisfies that zeta of 0 is equal to minus 1 by 2. It does look weird because zeta is a positive sum, but of course this zeta of 0 is not evaluated by taking this and summing over 1. In fact, this equals, in quotes, summation n equals 1 to infinity of 1 formally. If I put s equals 0, I get this divergent series. But zeta of 0 by analytic continuation is actually minus half. So I can make the formal replacement, summation of 1 is minus half. Now, I know that people find this very counterintuitive, but it's precisely analytic continuation, and entire lives of people from Riemann onwards, but I think also Ramanujam and so on in more recent, in the last century, Littlewood, Hardy, people like that, spent a lot of time, they have written books on this stuff. So we simply want to borrow these results. Now, how can we borrow them for our purposes? Okay, zeta of 0 is minus half, and zeta prime of 0 is known to be minus half log 2 pi. And that is this is the same as minus summation log n. Formally, this is the summation of minus log n from 1 to infinity. Good. Now, what we want to do is to take the product from n equals 1 to infinity of 1 by root alpha n. Remember our eigenvalues, now we are doing it the free particle, but we are starting again. Forget everything we did before. For the free particle, now we are trying to use this method to evaluate its determinant. We tried twice and it didn't work, but we are trying a third way and it works a little better. So remember the eigenvalues of lambda were lambda n equals what? I always forget the answer. Can someone help me? Minus I m something. Minus I m over h bar pi n over t squared, right? So this is lambda, so 1 over root lambda is what I want. I want det to the minus half. So that will have 1 by n times some constant, which I am calling alpha squared. So this is alpha. So alpha is actually precisely minus I m h bar, sorry, I m pi over 2 h bar t squared. Okay, so this is what I want the product of. Okay, but this I can write as e to the minus the sum. So product of something is e to the minus sum over log of that thing. So the sum is n equals 1 to infinity, and log of that gives me half log alpha from this term plus log n. And this first term is just, none of this depends on n, so it gives me sum of 1, and sum of 1 I replace by minus half. Yes?
Is it 2 over here?
Where's the 2?
So lambda n.
Ah. Oh, yeah,
And the alpha.
yeah, and I also forgot the n squared. I think this is correct.
Alpha cannot have
Alpha doesn't have.
Sorry, alpha doesn't have n, but the 2 is not there. Yes, I think the 2 is not there. Good. This half comes from the fact that it's square root of alpha there. Okay, so I simply plug in the values and I get e to the minus half log alpha times zeta of 0 times, and then minus, so this minus zeta prime of 0. And in the end, this is just, then I plug in that zeta of 0 is minus half and zeta prime of 0 is minus half log 2 pi, and my answer is alpha to the 1/4 over root of 2 pi. So a wonderful thing has happened. I've actually evaluated the determinant using zeta function method. Just analytic continuation, and I've got a finite answer. What's that answer? So det to the minus half O for the free particle, therefore, is equal to I m pi minus upon h bar t squared to the 1/4 1 over root 2 pi. Is this correct or it's not? Well, if you stare at it long enough, you'll see that it's not quite correct, but it has some correct features. So if we try to simplify it, first of all, it has I to the 1/4 power. That doesn't look good. The original answer was m by 2 pi I h bar t. Okay. So the power of h bar is wrong, the power of m is wrong, the power of pi is wrong, and well, the square root of 2 is right. But the most important thing is that the dependence on t is correct. T squared to the 1/4 is root t. So it got the t dependence correctly. And so here's one more lesson from this thing. If we use this heavy duty mathematical method to evaluate a determinant, we get a finite answer. It's not the right answer, particularly because it would not satisfy the composition formula, because only this answer can do that. But if I want to know how does the kernel depend on the time t, in time interval t, well, the correct answer says it depends as 1 by root t, and this answer says the same thing. Now, why is it important? Is it a coincidence that the power of t came out right rather than the power of m or h bar or something else? So here you should remember that m, h bar and so on are parameters of the theory, but t is not a parameter of the theory. T is the quantity I am calculating in a given theory. I am calculating the propagator over a time t, which is up to me. So that cannot be changed by a change of normalization, because the path integral normalization cannot have a t in it, because it doesn't know what t dependent quantity I want to calculate. So therefore getting the t dependence right is important, getting the rest of the dependence right is less important. Now we better leave this room, but I'll give you your quiz papers outside.